Welcome to a lesson on finding missing sides in similar figures. We might need to have a little discussion about what similar figures are. Similar figures are shapes that have the same shape but different sizes. Their angles are congruent and their sides are proportional. So the angles will always be exactly the same, but the sides will not be. The sides are proportional. That's the relationship they enjoy. Now, a similarity statement, if you can find one that describes two shapes, these are critical. For instance, if you have triangle ABC and DEF, look for a similarity statement. That's what you just saw that's been written at the bottom of the page. It says that symbol is triangle ABC. That squiggle in the middle means similar to triangle DEF. Now that's terribly important because now without even looking at the drawings, you know which angles correspond. And if you know which angles correspond, you know which sides correspond. In fact, sometimes the pictures can be misleading or not drawn to scale, but the similarity statement we can accept as fact. It's as law when it comes to solving for missing figures. So based on the order of the letters, angle A is going to correspond to angle D. Angle B from the left triangle is going to correspond to angle E because they're both in the middle. And angle C is going to correspond to angle F. Now similarly, if you look at the order of the letters, if you see side AB, that's the first and second letter on the left, they will correspond to side DE. Side BC would correspond to EF. Side AC would correspond to DF. And just follow the pattern of the letters from one triangle statement to the other triangle statement. So this time we actually have some measurements. I'm going to show you what it means to be proportional. Remember, the angles are the same. So if you know those two triangles are similar, the angles that correspond are going to be exactly the same. And it tells you the similarity statement, triangle ABC is similar to triangle DEF. So whatever angle A measures, angle D measures the exact same thing. Whatever angle B measures, so does angle E. And whatever angle C measures, so does angle F. They're exactly the same, but what about the sides? Well, I'm looking first at side AB on the left, and notice that corresponds to side DE on the right. So if you take their measurements, you can say that 2 corresponds to 6. Now let's find another set of proportional sides. AC corresponds to DF. So that means 2 corresponds to 6, that on another side. And then let's look at BC and EF. BC corresponds to EF, and that means 4 corresponds to 12. Now these are all equivalent ratios. That's what it means to be proportional. A statement that 2 ratios are equal. Even further than that, if you wanted to test it to just be sure they're all the exact same ratio, change them to a decimal. They're each going to be 0.3 repeating, or they would each go to lowest terms as 1/3. So having proportional sides in similar figures enables us to solve for missing sides. So notice I have this similarity statement written above the triangles. That's going to be very important. Now I have a missing side. Do you see the missing side is located on side HJ on the left triangle? Notice what HJ corresponds to in the other triangle. Look at the similarity statement. H and J are the first and last letters. They correspond to A and C. So A and C will be what your X corresponds to, and that's 5. Now I have set a pattern. That left ratio, I've compared the corresponding parts. X corresponds to 5. Now I need to complete another ratio with that same relationship. X corresponds to 5 in the same way that I need to go back to start with the left triangle and pick up 10. Now 10 is HI. The side HI corresponds to side AB, and so I say 10 corresponds to 3. Now it's really important. For the first ratio, I went left triangle to right triangle. For the last ratio, I went left triangle to right triangle. So x corresponds to 5 in the same way that 10 corresponds to 3. And then we know that if you have a proportion, their cross products are equal. 3 times x is 3x. That should be the same value as 5 times 10 or 50. And divide both sides by 3 to get 16 2/3. The missing side is 16 2/3. Let me back up just a minute. 5 is not the only thing that has a relationship with x. You could have said that x has a relationship with 10 and made that your first ratio, and that's valid. If you make that your first ratio, you'd have to say x corresponds to 10 in the same way that 5 corresponds to 3. And then if you still solve it, you'll get 16 2/3. Let's try another one. Okay, now this one, you have intersecting lines that form triangles. I'm going to put some angle markings on there to help us know exactly which sides correspond, because I'm not going to give you a similarity statement this time. You have a single marking angle and a double marking angle. I usually start with my missing value that I'm trying to find. That gives me a goal. So I'm going to place that in the proportion. Now, how do I know that x corresponds to 4? Do you see that x on the left side is between the single and double angle marking? Well, on the other triangle, 4 is between the single and double angle marking. So x has a relationship with 4 in the same way that, and I've set an order with that first ratio. I went from left triangle to right triangle, so my next ratio also needs to go from the left triangle to the right triangle, and that's going to be 0.5 or 5/10. Now, what does it correspond with, 3 or 2? Notice that 5/10 is located between the single angle marking and then one of those two vertical angles, and the side that corresponds to that is 2. Now I have a proportion that I can cross multiply. 4 times 5/10 is 2. 2 times x is 2x. Divide by 2, and your answer is 1. Let's see if we can find x again. Okay, now this is another one. It's like you have a triangle embedded inside another triangle. Do you see the two triangles? If you trace your finger along the very outside edge of that figure, that's the big triangle. Now put your finger on the tip on the far right and trace the smaller triangle. Do you see the smaller triangle? What I usually encourage my students to do is to redraw this figure with the little triangle written outside of the big triangle. Do you see the measurements for the big triangle? The big triangle measurements, the height is x. Look at the base. The base extends all the way across the bottom for the big triangle. In fact, it's 8 plus 12 or 20. 20 would be the measurement of the large triangle's base. But the small triangle's base, you have a height of 10 and a base of 12. So if I wanted to find similarity there, I can compare height to base, or I could compare height to height and base to base. Just make sure you keep the same order that you start with. So I've compared height to height of the big triangle to height of the smaller triangle. So now I need to compare something from the big triangle and small triangle to finish my proportion. And I have the bases, so I'm going to say 20 corresponds to 12. Cross multiply, divide by 12. The answer is 16 2/3 meters. That's the height of the big triangle. Okay, we're going to find x again. Now, without a similarity statement, this would be very difficult because they're turned in ways that are hard for me to tell what corresponds. But now I can tell A corresponds to L, B corresponds to K, C corresponds to M. I'm missing the X, so it's side BC that I don't know. BC, by the similarity statement, corresponds to KM, and KM is 2. So I went from left triangle to right triangle. I need to finish the last ratio in that same order. So x corresponds to 2 in the same way that 14, which is AC, corresponds to LM, which is 6. And now we cross multiply. 28 equals 6x. Their cross products should equal. And to find out what x is, I divide both sides by 6. So 28 divided by 6 is 4 2/3. Alright guys, watch this as many times as you need to learn how to set up your proportions correctly.